just want to give everybody an introduction to, what is this power IoT challenge that we are trying to address. And this is really all about trying to make batteries last longer for IoT applications. And there are three ways we can do this. And the first and the most obvious one is simply to design and to manufacture better batteries that are higher density, that can supply us more energy for a given volume. But there are two other ways that we should seriously consider, and we should look at all of these collectively. The second one is for us to reduce the power consumption of these IoT devices. So, make sure that we use the best available components, that we use digital interfacing to contextually turn these devices on and off, minimizing the drain on the battery so that a given battery will last longer. And the third activity, of course, is energy harvesting. That is taking ambient energy such as heat, vibrations, or solar energy, or RF energy can also be used, and converting these to electricity and using these as an alternative source to the battery, or indeed very often working in tandem with the battery so that we minimize the drain on the battery and make it last significantly longer. So this is then how Enables relates to all of this. We believe that not only do we need to develop technologies under our EU project Enables, developing the core platforms that I show here on the screen: energy harvesting, energy storage, micro power management, and system integration. But we then need to link these to the various IoT applications that we have in mind. So we have things like Industry 4.0, smart factories, smart mobility, various domestic well-being, healthcare applications, and then we have utilities. You've got environmental monitoring and so on. And this involves bringing in all of the stakeholders involved in this, not just the developers, but also the suppliers, the users, and the integrators of these technologies. So this is an ecosystem that we have put together, but there is one middle layer that is very important to this ecosystem. And it is, as I show here, we also need to collaborate with people who develop sensors, people developing next generation wireless communication systems, various technologists in the whole area of ICT, MEMS, and indeed NEMS, nanoscale fabrication processes, people developing low power electronic solutions, and indeed people developing microcontrollers, MCUs, which are at the heart of many of these wireless IoT edge devices. So this is the ecosystem as we see it in Enables, and one of the key messages from Enables is to get all of these people thinking about power and collaborating together to come up with the best system integrated solutions that maximize the battery life. So a quick introduction then to Enables. Enables is all about building the ecosystem that I just showed you here for powering IoT applications. It comprises 11 partners, as I show on the bottom of the screen there. We have ourselves in Tyndall, coupled with 2 divisions of Fraunhofer and 2 divisions of CEA in France, as well as IMEC in Netherlands. Then we have 3 Italian universities. We have Polito, we have Unibo, and we have Perugia. Then we have University of Southampton and also KIT in Germany. And these are the 11 partners in Enables offering 2 things. We are offering what we call transnational access programs, which comprise free of charge access to expertise in laboratories doing feasibility studies. And I'll explain exactly what these feasibility studies are in the next slide. And also doing things like joint research activities, collaborations amongst ourselves to develop system optimized and application oriented solutions, trying to come up with de-risked and standardized methodologies and library parts so that we can make devices which are system integrated, optimized, and give us the maximum battery life. So a little bit more detail then about the Enables Transnational Access Program, which is actually the biggest activity within Enables. And this is all about doing free of charge services for people, giving people access to our equipment, our tools, and our expertise to do power IoT related studies. These can be things like paper studies, simulations, early prototype development or assessment, can also be characterizations, or maybe given some guidance in terms of system integration. Coupled with the so-called transnational access feasibility studies, we also have a virtual access database of real-life vibrational energy sources that is managed by two of our partners, Southampton and Perugia. And this is a very, very useful database if anybody wants to get a feeling for what are the resonant frequencies and what are the real life ambient energies that can be extracted in many, many real life applications. And indeed, our offering is open not just to academia, it's open up to industry as well, no matter what part of the ecosystem you are, whether you're a researcher, a developer, an integrator, or you're working at the materials, devices, or the system level. So almost there now. Before we get into the studies, just like to point out that the four feasibility studies you'll hear about today are just 4 of over 60 transnational access programs we have actively in our pipeline. If you go onto our website here, and here's a screenshot, you will see many more examples of other studies that we are doing or that we have done. And also, if you look at previous webinars that we have done, you will notice that today is use cases 3. You will find, for example, use cases part 1 and part 2 as part of a repository of 16 webinars that we've done. So I would encourage you to go and look at those if you're not familiar with them. These are available for you to download and to watch. Okay. So with that, I will pass over to Peter, who will discuss with you the first of these feasibility studies. So over to you, Peter. Thank you.
Thank you, Mike. So I will share my screen. So now you should see my screen.
Yes, we do. Yeah.
Yeah, thanks a lot. So the application I will introduce to you is a retrofittable, self-powered and wireless screw monitoring system. So the motivation which brings us to this technical application is the fact that screw connections are used in numerous technical constructions. So as you can see here on the right side, they are used in wind turbines, they are used in pipelines, they are used in railway trains, they are used in any kind of big buildings. So a regular inspection of these screw or joint connections is mandatory. And of course, we get an advantage by permanent monitoring. The challenge in these screw connections is that the infrastructure for powering a permanent monitoring of such screws is often missing. There is no power supply for data transmission, and there is no power for supply for any kind of sensor connections. Furthermore, these screws are often used for mounting any kind of sensors. So screws show or are an excellent mechanical interface. And furthermore, and that brings us to the fact of energy harvesting, screws are also excellent thermal conductivity. So our vision in Fraunhofer, together with different other institutes, was to provide a screw connection as a fully integrated IoT device with a wireless self-powered force sensors. So this was the reason why we combined different technical systems in the washer of a screw. So we are using a piezoresistive sensor in the washer of a screw. We are using a wireless module in the head of the screw. This wireless module is an LPWAN system, which is able to transmit a low amount of data over a large distance. We also integrated an RFID interface in that electronic system for configuration and programming of that monitoring system. And of course, and this is the reason why I'm showing this example here, we are using a power supply which uses a thermoelectric generator, a battery, or a solar cell for powering the complete electronics. So here you can see the sensor element. We have 3 piezoresistive sensors with an offset of 120 degrees to detect any kind of reduction of the preload force of that screw connection. And by using 3 different sensors, we are also able to detect any kind of tilt or inclination of that screw connection. In addition, we have implemented a temperature sensor on that washer so that we are also able to compensate the preload measurements by the temperature. And in the electronic housing, we have an additional acceleration sensor, which is able to detect any kind of movement or vibration of that screw of that connection. For powering the whole electronics and the sensor signal processing, we are using energy harvesting and an optimized micro energy management. In one option of that screw, we are using a thermoelectric generator, and that thermoelectric generator uses that heat difference between the head of the screw and the environment. So if you're using the screw in any kind of object which gets hot or cold relative to environment, for example, a hot motor, a hot pump, or any kind of hot surfaces, we are using the temperature difference to power the complete electronics. We have a sophisticated DC-DC converter in the electronics so that we are able to work with smallest thermal gradients. So for example, a thermal gradient of 5 Kelvin between the head of the screw and the environment is sufficient to power the whole electronics and send the data every couple of minutes. An option is, of course, we are using a solar cell on the head of the electronics, or in cases where we do not have any ambient energy available, we have a rechargeable battery in the housing. So here are some performance data. For example, with a temperature difference of 25 Kelvin, we can transmit every 20 seconds. Of course, the minimum thermal gradient we need is around 5 Kelvins. With a solar cell on the housing of the screw or electronics, we get around 30 minutes transmission frequency in an indoor environment. In an outdoor environment with around 18,000 lux, we can use a transmission frequency once every 30 seconds. So to summarize my application, so depending on the application scenario, we have different options for power supply of these screw monitoring systems. Of course, the transmission time is controlled by the power, which we store in a supercap, or we could also program the transmission rate before installation. The main use cases we are presently addressing and investigating typically require transmission rates between 1 hour and once per day. And typical application areas are the screws in wind turbines, might be screws in bridges, on railway trains, or on any kind of construction equipment. So this was all from my side, and now I'd like to hand over to my colleague, Gary. Okay, Gary, we can see your screen.
Yeah, we can see it. Thanks.
Okay, you can see my screen now. Just thanks, Peter. So I'm going to talk about 2 energy harvesting real-world use cases. One is aircraft tracking devices, and the other is rotary machinery condition monitoring. In the first case, Tyndall has worked with Swiss Airtainer in Switzerland, and their application involves monitoring universal load devices. These are containers that are used on airplanes, and there's requirements here. Some are compliance requirements, some are safety requirements. Some of these unit load devices have their own temperature controls, particularly in the case of pharmaceuticals. In this application, present battery life typically only lasts a year to 18 months. And there's a great need to improve that battery life to more than 5 years, but at least double it to 3 years. So really what this Airtainer and the industry would like to see is to be able to locate the unit load devices, to be able to track them, to be able to monitor them, and for the ULD to send out an alert if something changes, and then to be able to respond to that. So the key technical components is being able to monitor the geographical location of the unit load devices and monitor critical data. And the ULD on a plane will typically communicate with an on-plane gateway, and from there to a ground application. Sensors that are required include temperature and humidity sensors, acceleration sensors, pressure, because the air pressure in a plane varies quite a bit with altitude. Sound of engine, sound of plane, electrical power signals, particularly 400 hertz, which is frequency used by airplanes. In terms of tracking, various approaches are used to track, are being investigated to track unit load devices. These include RFID tags, GPS, mobile, Bluetooth low energy, and also there's LoRa-1, which is a long range wide area network. So we investigated how to minimize the power consumption of the existing Swiss airtainer technology. We looked at emerging technologies. We analyzed the power requirement of current solutions, and we, working with them, envisaged an energy harvest powered system that takes ambient energy, harvests it, and stores it on combinations of supercaps, rechargeable batteries, and also batteries for backup. We also did some detailed work on an analog front end, which monitors temperature, humidity, acceleration, pressure, sound, light, 400 hertz. Typically, the analog front end senses these signals once a second, stores them locally, and then transfers them to a microcontroller infrequently, and then less frequently, the micro transmits the data wirelessly. That completes the first use case. So the second use case I'd like to talk about is work we've done with Mid-Sweden University in Sweden. And they've done a lot of work on industrial machinery. And in a lot of these cases, you have rotational shafts. If you have a high-speed shaft, then you'll readily generate a lot of AC power. But in the applications that they've been exploring, the shafts are operating at a low speed. So you don't get that much AC power. And then there's a need for a low voltage rectifier. But the good thing about shafts rotating is it's a very stable and common energy source. Variable reluctance energy harvesters consist of a rotating toothed wheel and a pickup unit. So this slide shows Mid-Sweden's University detailed test setup. The good thing about this type of energy harvesting is that what's rotating is just a toothed wheel, which is very simple. And the pickup unit, magnet, and coils are fixed. So those are in a fixed location. And as the toothed wheel rotates, then the reluctance of the system changes, and that induces voltages in the pickup coils. In the beginning, Mid-Sweden University looked at single-phase systems, but they've now moved on to three-phase systems. And there's a need then for to be able to convert these AC voltages to DC. So a typical application is where the wheels are rotating at 10 RPM. And in that case, the three-phase pickup units pick up about 0.3 volt peak signal from the three coils. Now, there's a need then to take this AC voltage and convert it to DC. So a common approach is to use a diode rectifier. The only problem with a diode rectifier is that there are two diodes in the path. And even Schottky diodes have a voltage drop down around 0.4 volts. So a diode rectifier won't operate above about 0.8 volts and won't work in this application. So then, working with Mid-Sweden University, we looked at CMOS rectifiers. And CMOS rectifier, you have both on NMOS and on PMOSs. And a CMOS rectifier can operate at low voltages. So we ran some simulations then using cadence vector and using a target process from XFAB. XFAB have a 0.18 micron process. It's a very good mixed signal process used in a lot of power management applications. So we simulated with Spectre the three-phase AC signals, and then we simulated the CMOS rectifier. So we're seeing the CMOS rectifier operating at the 0.3 volt peak to peak. And we looked at a lot of different conditions, but one condition is where the load resistor is varied. So we have a 0.3 volt peak voltage in, and as we reduce the load resistance, 250 ohms, then the output voltage has dropped down to about 0.22 volts. And at 750 ohms has risen up to about 0.28 volts. But the output power that we're getting at 500 ohms in common load is 200 microwatts. And the efficiency of the CMOS rectifier is 85%. So this block with the harvested AC voltage and low voltage rectifier gives us harvested 0.2 milliwatts, which then can be passed to a power management unit to provide a stable voltage, DC voltage of something like, would typically get boosted from this level up to about, say, 1.2 volts. So that completes my presentation. Thank you. And I think questions are going to be at the end.
Thanks, Jerry. I think we'll move on to Gert. So.
Yeah. Thank you very much, Gary and Niklas and Peter, of course. So I hope you can hear me soon. So I will start my presentation. Please, a second to give me the start and sharing the right screen. Where is it? Here. Okay. So hopefully you can see the first slide. Can you see it?
Yes,
Someone?
we can. Yeah, we can see it.
Thank you very much. So RF energy harvesting and smart building applications. Yeah, so let's go on here with this topics. Last time in the webinar where we had these use cases, I told also about the smart home application here, the fully integrated window sensor. This was powered by photovoltaic, completely integrated in the glass of a window, for example, as a special feature here with sensors in it that make it completely independent from every other sources for this special purpose. But the light harvesting is not suitable for every sensor what you have in your house, sensor or actor. So we have this vision here that we can create batteryless sensor environment and sensor network inside the complete building. Is it a smart home or another building, office building itself can be very similar. So what you see is a lot of switches, of course. That is the most simple sensor switches for lights, or switches at the door or the window that might detect if it's open, closed, or locked. Even at the furniture, you can have something, but also other sensors from temperatures for heating control and things like this. Yeah, here the idea is to completely avoid any batteries for this. So how can be done this? We are looking beside these photovoltaic harvesting also to RF energy harvesting. So what has to be considered here? From the frequency, we need some supply there, area wide or cellular frequency availables there, where the power level is high enough to power such a thing. I'll come to some figures later on. We have to use the right frequency, having higher frequencies, then the attenuation rises. That's physically not quite right, but we can say it in this way. It's easy to understand. We have the induction, that means the voltage generated by the antenna rises with the frequency in physical sense. Also there, the real values of elements there are a little bit against this. Then we have antenna sizes decreases with frequency. That's a good option for higher frequency. So we have to find a compromise how to use frequencies and how to dimension systems in this. Then the distance, of course, if we have a specific distance to the power source, that means the transmitter, of course, the field strength decreases with the square of the distance, and the bandwidth is also interesting for energy harvesting. If you have a high bandwidth, it might be possible to use several transmitters for harvesting. That means to utilize the energy from multiple transmitters there. That are some topics that can be taken into account for dimensioning such a system. Frequency in general, what's available there? We have, of course, these very low frequency that's coming from the grid, from our power supplies, but like mentioned before, the frequency, the induction, that means the voltage generated from the antenna here in correspondence to the frequency, and that's very low. That means these frequency of coming from the grid are too low. Or on the other side, you need two big antennas to harvest anything from this frequency available there. Then we have these radio transmitters, the audio broadcast is from long wave, ultra short wave up to the newer DAB. They are available everywhere, of course. Then we have the TV, either terrestrial or satellite TV, but everything what's coming from a satellite TV or GPS, they are such low they cannot be used for anything else. Perhaps if you are close enough to some of these transmitters, that might work. GSM, any kind of the cellular phone or this mobile phone might be also an option if you're close enough to this, and any other frequencies are also available. But today I don't want to go too much in detail of these available, everywhere available frequencies, because they're rather low. You have typically, if you have these radio transmitters, power levels from -50, -80 dBm. That means it's nanowatts available, and that's a typical. It's too low. You can discuss about Wi-Fi, this wireless LAN Wi-Fi. might be an option, but here you have the duty cycle that's also restricting here. But RFID and these things are one way to go to transmit a signal into your surrounding, what can be used here for energy transmission. So this is yeah, from my colleague from University of Southampton, Mohammed Wade. I've borrowed it from this nice slide to bring to show how it's working. You have this transmitter, and on the other side you have the energy harvester. And from the transmitter is coming the signal as a wave. If you are far away, you can see it's plain wave coming to the antenna, and you can calculate the power density with this formula, where the dependency is the distance from the antenna to the power transmitter. You have the power level itself coming from the transmitter and the gain from the antenna. So you can calculate the signal here at the antenna. That's this power density with the effective area of the antenna, and that gives you the power available. And you have the rectifier here. That's some losses in the rectifier, and that's a DC power then you can use here. So this, like mentioned before, is also limited. Here some peak transmission by regulations is available. And if you have the dependency over the distance for a specific case, or more or less a typical case, for example, the UHF band, that's where the UHF RFID takes place in Europe, around 866 megahertz. In US it's 915, and Japan is a little bit higher, but it's for the energy point of view more or less the same. Transmit power, it's more or less also the same in every country. We have here a little bit more than 1 watt transmit power. And if we have a look to the power over distance, where the power at the position of your sensor, of your tag, for example, you have about 8 meters, then you have at this position the power of minus 18 dBm. That's calculated, in other words, that's a 16 microwatt. Or in other words, if you reduce this by the losses of the rectifier, it's about 14 microwatts. The rectifiers today are rather good. You have 5 to 10%. I've calculated a little bit more than 10%. What is the loss of your power at the rectifier? And then it's available in this area. That means if you have a circuit running with 1 volt operating voltage, you have 14 microamps to power a controller, to power a sensor in that specific distance. Of course, you can vary this distance closer, you have much more power. And this is, I think that's about this, will not say limit, but a practical limit where you can see that. So if we are now using this for our sensors, we can go to these RFID principle. We can also use only the energy transmission and having an active sending transmitter at the sensor, but the RFID has the advantage that you don't need any power for the transmission of data. That can be done with this RFID principle. That means the backscattering, that what you do here from RFID use, only changing a little bit in your matching circuit. That means you are changing the load, what the antenna sees here, by the by the clock of the data coming out of the chip to be transmitted. And this can be recognized in the reader unit. That's on one hand side the transmitter for the power and the receiver for the data. So that's a good way to use this RF signal. It's perhaps not only energy harvesting, that's a continuous way for energy transfer and sending back data, but you can also add here a harvesting device that you can collect the power and doing sensor measurements and transfer it back later, for example. This comes a little bit later. Here also some numbers very similar. It's a bit calculated with a closer distance from the tech to the reader here. It has a little bit higher power. So what we've done there is to realize these kind of switches. For example, at the window. At the windows, typically you have these handles. They are used for open, close, different positions of the window. And there is a mechanic inside the frame of this window. And the frame is equipped then with a permanent magnet. And this magnet, depending on the movement of the handle, is going around this reed contact here. And there are already RFID chips available at the market with the with switches for this purpose. Not the switches included, but you have an open I/O, let's say an I/O pin that can recognize a kind of switch. And these very simple sensor has nearly the same power consumption as a standard RFID chip, where RFID is only used for identification. Here you have the minimal offset of these additional power. A little bit of additional power. What you need is for reading out of this sensor here. So you can manage this, and this works very good in the sense that you have the readout of the switch over a distance, for example, from 8 meters, can be more. It's trimmed a little bit here from the antenna. That's actual status in the moment. There is also work be done to optimize the antenna, to optimize also the energy harvested there for this switching element. So the next step is then having a real sensor. We've done this in a kind of evaluation kit. We have built up electronics board with an RF front end for harvesting and also for communication. Some blocks here of power management controller. You can see it here on the photo, what we have for testing it, a controller type with some external inputs, with some prepared inputs for sensors already on board and to be connected here. And for testing purpose, you can also equip it with a coin cell battery to have an easier debugging and development. Yeah. So what is the power consumption for this case? For example, if we are operating a temperature sensor, then we have a power consumption for the conversion and statement machine of about 20 microwatts. So that's a little bit more. Of course, that's what's needed for these simple switch. So this allows of distances a little bit less than these 8 meters. What I've mentioned before, from this 8 meters, we have only these 14 DC power consumption here. So the capacitor can measure it. You can have some caps to do a little bit energy harvesting. Then you can harvest energy. Then here this capacity with the RF module that you can also extend a little bit the reading range. But it's not more than this 8 meters because there is a threshold so that you can extend then the harvester there. Pressure sensor as a second example shown here has much more factor of 10. So, but typically pressure sensors are not used so often in a building only for ambient pressure. That's I think not dependent of the position that can be placed if you really want close to the reader, but not this very often used sensor. Other sensors are light, perhaps. You can imagine something is also available. Air quality. They also need some more power coming also in this area. So far, thank you very much. And I think we are going for questions and answers.
Yeah. Thanks, Gert. I think we'll move on to Pratik, if that's okay, and then we'll have the Q&A later.
Yeah, I think I'm audible.
Yeah, we can hear you fine.
Yeah. So good afternoon to all of you. So the transitional access that I've been working on is based on the structural health monitoring application. So this is basically the introduction to the structural health monitoring, where we try to detect structures for their damages, safety purposes, provide maintenance and rehabilitation of advices, improve the design guidelines and disaster mitigations. So basically SHM has following applications in building and bridges, tunnels, wind generators, or any critical structures for that matter of fact. So the most of the challenges that we face in structural health monitoring infrastructure is basically we have to have a reliable service for a longer period of time, following major technology changes, spanning several generations, and experiencing dramatic evaluation. To develop a wireless sensor network for structural health monitoring purpose, it needs to be a reliable one, an energy aware one, and of course a smart one. So with this transitional access comes from Ulster University. So what they were trying to utilize is a neural network into structural health monitoring. So basically, they use energy harvesting as a power source, detect anomalies, and reroute the data, that is temperature, vibration, pressure, and displacement sensors. So for an example, in 50 years of monitoring a bridge, even if 5 to 10% of the wireless sensor fail, can the remainder of the system still gather the data and supply sufficient information? So that is a question that requires to be answered. So in case one of the sensors in a sensor network fails, how the rest of the system will respond to it. So they have used a neural network that can help in order to improve that system. So the initial structure of the design goes with a big little architecture, where we have a big processor and some little processors connected to it. So these little processors are basically small sensor nodes, and they are actually getting the data to the big processor. So what happens if one of the little processors that is gets destroyed, or is it not working? The big processor then reroutes that data from the other little processors. So taking these into account, now this big processor will have the artificial intelligence, that is the neural network code running on it. So it will have a bigger battery, and while the little ones will require energy harvesting applications. So the key scientific challenges which we have in this one was to investigate how to minimize the power consumption of the existing and emerging technologies. Should we include the context of power awareness, turning on the sensors when we are needing it, and turning it off when we don't need it, analyze the power requirement of the current solutions, and investigate the available ambient energy harvesting solutions. So in this feasibility study, which we started in December 2021, we had first we understood the concept which they were developing about the little big architecture. We tried to develop a simulation tool to help them optimize the little and big processors. Then we would implement the neural network that they have made in order to analyze the power consumption of the bigger processor. And most of our this work would be focused on taking the power as at the front of it, because we need to provide them efficient power solutions to last the entire lifetime. So we started off development with the Matlab simulation tool. I was able to crawl through the data sheets and perform a simple tool that could help us select a microprocessor for this application. So the tool goes like this. So this is the first screen of the tool, where we can enter the manufacturer name and the processor names. We have to enter its power consumptions, that is sleep, sensing power, and the transmission power. And of course, the timing duration of sensing and timing duration of transmission. So at this instance, we have 5 processors that we've included. So 5 are from Analog Devices, ST Microelectronics, Infineon, and Microchip and NXP. So all these 5 processors data have been included into the tool. On the second phase, we try to calculate the power consumption. So how do we do that? First, we select the processor we want from the database. After the selection, there's an option for the user to enter the sensing interval. Sensing interval basically refers to the time duration you want your sensing to take place. So in the example that you see, the time that is given as 900 seconds, this is basically referring to every 15 minutes. So after every 15 minutes, we are trying to sense the data. Similarly, we have to transmit the data to the bigger processor. So we have included a transmission interval, which is also similar to the sensing interval in this example. So once you click on calculate, we are able to calculate first the number of senses there would be in a single day. The second part, which is the most important one, is the power contributions. So as you can see, the power transmitted for the transmission part, the power that is contributed for the sensing, and the power that is used by the sleep mode, and the total power are being shown. The last part of this tool is the plot, the button that you see at the last end. So this plot that helps us give 2 plots. The first one that you see on the right side and the left side is basically for going from 0 to 3600 seconds, which is basically an hour. The second one that you see is going from 10 to the power 0 to 10 to the power 5. That is basically for a day. So this goes from 0 seconds to 86,000 seconds. So what this signifies, 10 to the power 0 means that you are sensing and transmitting after every second, and 86,000 mean that you are transmitting and sending once in every day. In case we zoom on to the middle portion, we mostly utilize this values of seconds from 0 to, let's say, 2 minutes, that is 120 seconds. So yeah, so we can see the zoom part, and we can see as the duration increases, sleep power becomes more dominant, and the graphs goes to reaches almost 0. So that is the function that we are able to implement. In future, we will be implementing this neural network onto the bigger architecture, onto the FPGA, and try to analyze the power. Thank you.
Yeah. Thanks, Pratik. I think just before we go to the Q&A, I think Mike wants to make a couple of announcements about some news about Enable, some conference, so on. So we'll do that. It'll take a minute, and then we'll go into the questions and answers. Are you okay there, Mike, to share? Sorry.
Okay, is my screen being shared on, Nicholas? Yeah,
we are fine. Yeah, thanks. Yeah, go ahead.
Yeah, very good. Good. Okay, so just 2 more minutes of your time, everybody. So thanks, everybody, for staying with us. I just want to point out that we have created a position paper which we published last year, which is available via our Enable's website. That is there for everybody, talking about the importance of the IoT ecosystem and the importance of the feasibility studies, some examples of which you've seen here today. So I don't expect everybody to be able to read the small print here, but here are some key messages. Here are some key testimonials from previous feasibility studies that we've done. So for example, a Swiss-based multinational said to us, with the RF energy harvesting technology, we plan to expand our portfolio and serve a much bigger market in the future. We had another example then whereby we had an Italian university telling us that with the Realize prototype, we aim to optimize power harvesting for millimetric frequency range IoT devices, where there is a huge surge of interest from commercial partners. And then we had a Dutch SME telling us that this will result in materials that can deliver more energy in real life applications. Here are 1 or 2 more examples. A US SME told us that this gives us a solid basis for characterizing and optimizing power consumption for our next generation of devices. 2 further SMEs, one in Austria, telling us that the technology will lead to a commercialized product that increases the safety of assets and goods and ensures on-time delivery. And then finally, an Irish SME that said that the feasibility study showed intervals would enable us to activate self-cleaning sensors. So you can find out more on our website. You can also find out more about these on our enables position paper. The link is there, and you will find this in the slides. And you will find many, many more examples, not just of the TAs, the transnational access feasibility studies, but also many of the joint research activities that we've been doing amongst the 11 partners within Enables. And indeed, you will find many examples of these in the previous webinars as well, which are available for you to view via our website. Then finally, just a quick plug of one important event called NRHARF 22, where Enables is a technical sponsor. This is a gathering together of Power IoT stakeholders, such as we showed in the slide here, getting together, sharing information, sharing knowledge, giving updates regarding the latest technology developments, giving examples of real-life use applications. In this workshop, we will have presentations, panel sessions, demos. Enables itself will have what we call a carousel of feasibility studies, like what you've seen here today, giving many more examples. So if anybody is interested in this, please check out the NRHARF website. And indeed, we are also inviting people to give us posters or demos for NRHARF as well. And that registration option is open for you as well via the link we see there. So NRHARF 2022, 5th to the 7th of April in Raleigh in USA, all are welcome. And indeed, I know many people on the call are already planning to go, and in many cases presenting posters or demos or indeed presentations. So that's it, Nicholas. Thanks everybody for attention, and we'll now pass over for Q&A.
Yeah. So I'll start. We already received a question on the chat, so I think I'll try to show that now there. So it's for Gerd. So see if we can should be coming. Can you see it in there, Gerd?
Yeah, I can see it. So, is one of the second of energy harvested a significant reduction of the harvested free? In other words,
Michael, if you are online, could you? Yeah, maybe we're trying to find it a bit hard to understand. If you are online, could you please?
So my understanding here regarding interference also, is RF a possible source of interference? So what we have to know is the use of the frequencies is very good regulated. So if you have any device, if you have if you do any transmission there, you have to fulfill the requirements, because every device is tested and gets an assessment before you can sell it as a product. And here we have the frequencies. What we are choosing for energy harvesting is typically what I mentioned, the UHF. This is special band where you can, where it's allowed to radiate a signal with a specific power level. There are some bands available in the low frequency, high frequency, the UHF, ultra high, and also SHF is the super high frequency at close to 6 gigahertz is also a band, and also higher frequencies at 60 gigahertz are available for such a purpose. But these very high frequency, they are not useful due to the effect that with higher frequency, the attenuation, what I said in the beginning, is very high. You don't get any distance for energy transfer. So the most convenient one is then this UHF frequency, and there it's allowed, but also with the duty cycle that I've forgotten to mention. you are not able to have a continuous signal. So there are many approaches also to use other frequencies available, not especially the original intent for energy harvesting, but you might use them, what I mentioned, for example, this Wi-Fi signal. But also there you have these duty cycles available where very short times where the transmitter is on power. So the RFID is still the one where you have the most possible power to be transferred, where you can have typically this 10% duty cycle, and you can do a lot of energy harvesting with the signal. But from the purpose of energy waste and from the system design, you should have an eye to the power of the power transmitter, of course. So today, of course, there are high efficiency power amplifiers available with this new technology, but at least you have a few of watts what you are using of power to operate this transmitter, this device. So in every case, it's a good idea to save as much energy as possible and don't transmit too much power. Yeah.
Thanks, Carl. As it happens, it looks like the RF is the area that has having the more interest for. So we have another question: is do you offer an RF energy harvesting evaluation kit?
Yeah.
Yeah, it's in the chat. Did you want to have a look?
Yeah, I see. Do you offer the evaluation kit? Yes, we are working on this. Please send me an email. Do you have it? If not, I can send me an email and then I can see. The kit is not the problem. You need some documentation for this. This is on progress. So I would like to gather everybody who is interested, that we can send them the information out, or please send the request to Niklas. He has
you can send it to me,
so
and I'll forward it to Kurt. That's fine. Yeah.
So I can give you information about this.
Very good. Okay, thanks. Is there any other? Oh, there's another one that just came through the chat. Are CMOS rectifiers at the moment recent research, or are they already available commercially as integrated circuit?
Yes, yes. Typically, you have a special circuitry for the rectifiers. These are CMOS-based transistors switched together for these rectifiers. What you have to consider compared to the classical diode technology is the threshold. What you need on one hand side is a low threshold, but also low leakage. So these are typically some trends running against each other. So, but mostly they are realized with this transistors, CMOS transistors. That's quite right. Yeah.
Very good. Okay, thanks. Is there any other questions? You can put them on the chat, or you can turn your microphone and your camera on and listen to it.
Yeah, and please also use our Enables website if you think of a question afterwards, yes. Or if you're viewing this and not live, please send an email to via the Enables website to Nicholas or to one of our colleagues.
Yeah, if you send a message to the message, yeah, I'll either pass it to the speaker or I'll try to reply myself. Thanks. Look, I'm a bit aware it's already past 3, so we'll be at it more than an hour. So I think I would like to again thank you the speakers. I think they were very interested at real applications, and then also obviously to all of you who attended. And as you're watching it recorded, I hope you learned something out of it, and that if you have any questions or anything, come back to me and we'll try to send you a reply. Okay, thanks everybody. Take care.